Hi, I'm Aaron from Living Science Videos. Think about what would happen if you left your bicycle outside exposed to the weather for a year or so. It would be subjected to heating and or freezing, and the temperature of each of its materials would stay close to whatever the outside temperature is. It would also be subjected to rain. And the important thing to remember about rain and your bike is the effect that water has on chemical elements and compounds. Water, as you know, is H2O, so each water molecule contains one atom of oxygen. Oxygen is a highly reactive gas, and when it forms compounds with other elements, it's called oxidation. When it happens to your bicycle, it's in the form of rust. But oxidation can also take the form of fire. For example, the Hindenburg was a balloon-like airship which used hydrogen gas to float because hydrogen is lighter than air. It's the lightest element there is. But hydrogen is also highly flammable. It seems a spark set it off and the Hindenburg erupted in flames. It was the worst aviation tragedy of that era. The Hindenburg disaster was the most famous hydrogen explosion. What's chemically interesting about hydrogen when it's on fire is that it's combining with oxygen. Hydrogen combined with oxygen can make hydrogen peroxide or hydronium hydroxide, but it usually makes dihydrogen monoxide, also known as dihydrogen oxide, or more appropriately, hydrogen hydroxide. But most of us just call it water. In other words, the massive fire from the Hindenburg produced a large volume of water vapor instead of smoke. This fire eventually turned to rain. Chemical reactions often produce heat energy or changes in color or texture as the reactant chemicals turn into their products. That's why your bicycle chain changes color when it's left out in the rain. Oxygen mixed with the iron in the steel produces iron oxide, which is a corrosive. So your rusty old bike is going to start falling apart. Anything subjected to air and water is subject to weathering. Usually anything that moves or is active but isn't alive tends to run out of energy, stop, settle, cool off, and get broken down pretty quickly. So why doesn't the same thing happen to living things like centuries-old trees or yourself? How do you keep going even after other things would have stopped? Living things, organisms, have a number of automatic defenses and processes to preserve, prolong, eliminate, and replenish chemical components and thus maintain some balance in their internal structure. For example, the keratin filaments made of proteins in your skin have just the right shape and elasticity to expand and absorb some water, but not too much. If you ever wondered why your skin gets wrinkly or prune-like when it's soaked in water, it's because the keratin filaments in your skin have elastic properties that can expand to absorb water, but your skin also reaches a point where it can't absorb any more water, and this is like when you stretch a rubber band and it returns to its original shape. If it didn't return to normal, then you would still have prune fingers today, even after all of the times that you'd spent too much time in the bathtub or in the pool. Your skin defends you from absorbing too much water, but it also absorbs the amount of water you need, all without you having to think about it or even having to thank it for doing its job. And your skin has other functions too that help keep you at the right temperature and other fascinating things as well. Unlike your bike, your body has systems that maintain your temperature despite what the temperature outside is, and also your bike can't defend itself against long-term effect of water like your skin can. Your skin is part of just one system in your body. There are other systems that help keep you functioning and healthy, and these systems are made of cells, each with a different role to play in keeping you alive. Living cells are made up of one or more cells. Each of your cells is part of a larger system. At the same time, each of your cells has its own system to help maintain it and keep it alive. The big difference between living things and non-living things, like your bike, is that living things maintain internal stable conditions that are necessary for life's functions, what we call homeostasis. Think of that as home stays as is. Now think about it. How could your larger systems that keep you alive function if the tiny cells that make up those systems could not maintain their own stable internal conditions? Without homeostasis, your skin would break down under weather conditions like the metallic parts of your bike. Each of your cells have different tiny parts called organelles. Like the organs in your body, the organelles in your cells have specific functions. For example, your lungs process oxygen that your body needs to create chemical reactions and produce energy. It's called respiration. Cells also have a type of respiration, which we'll explain later. The chemical reactions in your body are, of course, much smaller and safer than the Hindenburg's hydrogen and oxygen, so that you don't explode. People don't spontaneously combust, but you do get the energy you need to keep you alive and kicking. Your lungs and all your other organs are made of cells that help perform the functions that keep you healthy, and your cells have organelles that do the same thing for them, but on a smaller scale. In the next video, we'll show some of the functions your cells use to maintain homeostasis and the organelles that carry out those functions.